Okay, here's our outline for today. And welcome, everybody. Glad to see you back after the weekend. Um, we're going to review one of the homework exercises. And I frequently do that, not all the time, but sometimes. And I'm going to do it today, even though I know that when I looked this morning, a good fraction of the class had done the homework, number one. And they had done pretty good on it. So, but we're going to review it a little bit. Before I do that, though, I want to go through the concept of early iClicker registration. We just synchronized the roster just now. Caroline did it. And so if you're registered on iClicker today, you will get another bonus point. Now, some of you were registered last week. And I synchronized I thought it would be Thursday afternoon, but it ended up being Friday, I don't know, about 10 in the morning that I got to it. Anyway, whoever was registered by that time Friday got an extra bonus point. And it shows up, for those of you that are newbies to Canvas, it shows up with a little blue alert symbol here to signify that you have a new grade. And when starting again. Anyways, when you guys get new grades, sometimes you'll have 3 or 4 of them there if I have a lot of grades uploaded and stuff. Anyways, you click on the grades tab and it'll look something like this. And down here, I forgot to make my cursor gigantic. Hold on a second, students. We have to have a gigantic cursor. Okay. Yeah, so it's right here, early iClicker registration bonus. Close up on it. Right here. And you see I've got it set up for today, January 17th. So hopefully a bunch more of you will have bonus. And if you already have this one, you have the next one too. In fact, you have all the other 4 ones. I haven't posted them yet, but you will get them. All right, so that's good. And the amount of bonus pointage that you get is 1 point. Now, I'd like to point one thing out here to you in passing, and that is that when you're talking bonus points, the out of number is always 0. All right? That's basically what defines a bonus point. In other words, when you take a test, it's a score out of 50. And if you look up here at homework 1, it's a score out of 5. So, and homework 0 was a score out of 1. Now, homework 0 is not part of your homework points for the semester, but homework 1 is, and there were 5 of them. So if you don't get 5, you don't get full pointage from that homework. All right. But now, so you can think of these things as the denominator, as going into the denominator, if you're trying to figure out a percentage. Okay. Now, on this one, for a bonus point, bonus points do not affect the denominator of the percentage. They only affect the numerator. Right? That's why that 0 is always there. Okay. Now, questions about that before we continue? Yes. Yeah, I uploaded them Friday, and if you didn't get it, that means you didn't register by like Friday 10 in the morning. But I noticed that over the weekend, a bunch more people have registered. So as soon as you register and then we have class, you'll start getting those bonus points. Up to? Yeah, come see Caroline or Darian after class, and they'll try to get you sorted out. By the way, for those of you that are Macintosh or iOS users, iPhone, iPad, MacBook, etc., apparently Safari is nasty for registering. Oh, speaking of nasty, there's a bunch of you that are not sitting in the first 5 rows. I'm going to have to start bringing the campus police in here to, dude, no. No, no. The front, no, you can't sit in that row. I want people in the first 5 rows. All right, slide on over here. The rest of you guys, it's a 5-yard penalty, and I'll try to do the down over on Thursday. But anyways, try to remember that first 5 rows. Now, what was I saying? Safari. Yeah, Safari is problematic for registering. Not sure why, but supposedly Chrome is good. Now, the reason I don't know for sure is because Canvas is itself troublesome in major ways. In the old Blackboard system that some of you may remember, either from UCF or another school, we used to have a student account that that really did work like a student account. Now I have a student view, and unfortunately the student view does not work. And this is student view. See where it says grades for test student? That first name test, last name student is my student account, and it doesn't really work the way your guys's does. So in other words, I can't use it to register an iClicker. So I can't really see how the iClicker registration page works, but from what I hear from my TAs and from other people, using Google Chrome will work. And there's all kinds of security. It used to be the big problem was Microsoft Internet Explorer, but and all the security settings and so forth. But now it's Macintosh Spark. You had to enable what? Cookies?
Yeah, like I don't know what it is, but it's something on a website.
Yeah, it's always something like that. Yeah, because I have cookies disabled for only. And then disable them again. Yeah, okay. All right. So maybe if you want to try Safari, try enabling cookies and then register. And when you register, it'll return a little table. You know, the top row is black and the second row has your information in it, you know, the serial number and I think the date that you registered. And that signifies that, yep, we got it. Okay, so if you have that, you're good. And then you can go and turn off cookies, I guess. All right, any other questions about iClicker? In the back. What? The app?
The iClicker app.
The iClicker app? And, oh, you have to have an actual physical. Yeah, other classes are using, it's called Reef. And, yeah, I know that it's out there, but we use these babies. All right, principally because Reef is, from what I understand, it's not that, it doesn't have the capabilities that I need. And but I don't know, some instructors like it. But yeah, so just do you have this? Do you have one of these? Okay. Borrow one from a friend. It's perfectly fine. But it's got to be iClicker 2. iClicker 1 was just A, B, C, D, E for multiple choice. This one allows you to type in numbers and letters, and we will need those for this class. Probably Thursday, we'll do some calculations together and some more deluxe questions. Okay, does that answer your question in the back? Good. All right. You had a question?
Yeah, my remote ID is kind of faded out.
Oh, okay. If the remote ID on the back is faded out or rubbed out, which can happen, plus they're really small, so you need a microscope to read them anyways. So if they're rubbed out or you don't have a microscope, what you can do is when you turn it on, it flashes the serial number. Matter of fact, you can see it, but you got to do it a couple times because by the time you write it down, half of it'll flash back to the ready state. So, yeah. So, but you can always get the serial numbers from the display. Okay. All right. Now, let's start talking about physical science, physics. And our topic was motion last time. We're going to be extending that today. But before we do that, I want to share some information from a recent reading that I was doing actually last night in a traffic safety course on the internets. I don't want to tell you why because it's embarrassing. But they had all this cool stuff about, accident prevention and stuff like that. Why not to speed? And they had this quote here: if you're driving fast, your stopping distance is greater. If you double your speed, your distance required for braking will be 4 times longer. Not double, but 4 times. Now, we're going to understand in a few weeks why that is the case. And so I was reading that and I thought, boy, this is one of the good things about this course that I'm taking, that it actually has a lot of physics in it. Here's another one. They have this, and this is actually a screen grab. If you're speeding, which I know nobody in here does, you're all nice citizens and so forth. When you're speeding, and down to the 4th bullet, it says your force of impact in a collision is much greater. And then the last phrase, by increasing your driving speed by only 10 miles per hour to 35 miles per hour, the force of impact doubles. Now, we're going to understand the force of impact as well. Not this week, but maybe next week. All right? So that's on our horizon. And so now, hopefully, none of you will have any, what do they call them?
Traffic citation?
A traffic citation or a moving violation where you're necessitated to take a traffic course. So you won't have to do this. But if a friend of yours does, you'll be ready to tell them how to do it. Because all this stuff is easy money in physical science 1121. So what we learn is important. Now, last time we talked about Galileo quite a bit and his conviction that the universe was not random and that it was actually like a grand book, an enormous book that was written in a mathematical language, and the emphasis being mathematical. And from that conviction, he built up himself this entire enterprise that we call science that is designed to work in that language, and of course, Italian, English, and all the other vernacular languages, the natural languages, as well as the mathematical language. It's designed to be an observational and a measurement-based activity. And in fact, as I mentioned last time, and what I really want you to think about extensively between now and 80 years from now, is that your students at Galileo School, just by studying with me, and we're following in the footsteps of some mighty scientists. Galileo was number 1, but here's his number 1 student, Sir Isaac Newton. And so he was a student in the school, and we're just following in his footsteps. And another thing that we talked about last time was how to calculate a distance and a speed. We discussed how to calculate a distance from coordinates of 2 positions that you're trying to, so maybe a right triangle, or maybe just a subtraction, x2 minus x1, or in this case, xb minus xa, the positions, the coordinates of positions A and B in the x-coordinate system. We also talked about how to calculate the elapsed time, delta t, based on the readings from the clock as the object passes by position A and position B. So that would be delta t equals t subscript B minus t subscript A. Dude, I see you taking a picture with your iPad. All this is on YouTube. You don't have to worry about that. You can, you're not in trouble or anything, but I'm just saying, everything's going to be in YouTube a little bit later this afternoon. So, and just so you know, you guys, everything is in YouTube, and using YouTube to review the lecture is a really good study. This is the person to talk to about studying from YouTube. Darian used that extensively, and she has been TA for many semesters now, and she crushed my exam several semesters ago, the semester before she became a TA, and she used YouTube extensively. So why do I bring that up? Well, in this class, because we have YouTube, you don't have to furiously take down notes, verbatim or any other extensive notes. Just take down the basic information and then go fill it back, fill in the rest of your notes to your heart's content and as slowly as you want using YouTube, and it will help you. Matter of fact, even if you do it with a friend, it's even faster because you can talk things over as you do your notes. Question? Yeah, the link is in Web Courses. It's on the homepage. And last week's lectures are already up. I do them after the noon lecture, so somewhere between 1:30 and 2:30 usually your YouTubes are up. Now, we use the speed definition to actually get a speed, and that's the big formula up here, delta x over delta t. We also had it on homework 1, and so this is where I want to review number 3 from homework 1 with you, because it was just a simple calculation of speed. Most of you did pretty well, but let's just take a look at it and see what we can see. All right. So here's the picture that we had, the picture of this guy that's walking into a door, unfortunately. Here are the data. Down here, event 1 and event 2. Here's a close-up of it, and you can jot that down in your notes if you feel like it. Event 1 happened at position negative 2.45 meters on the x-axis. So that means somewhere off to the left. And that's the time when you started your clock. So T1 equals 0.00 seconds. And then event 2 happened at the door, 0.0. So the x coordinate axis had its 0, the origin, right at the door where that guy ran into it. And the time elapsed was 0.74 seconds. So T2 is equal to 0.74. Now the calculations are here. And as I mentioned last time, when you're doing delta t or delta x or delta y or delta anything else, it's always later quantity minus earlier quantity. So for delta x, it's coordinate x2 at the later position, which is 0, minus the x coordinate at the earlier position, which is x1. And that was negative 2.45. Now, the reason I bring this up is because I want to remind you and emphasize that subtraction of a negative is like addition. All right? When you subtract negative 2.45, that's like adding 2.45. So the total over here for delta x is 2.45 meters. That's the total distance along the x, or the total displacement along the x-axis for this individual. Now, similarly, the elapsed time, delta t, is T2 minus T1. All right, so the latter time, 0.74 seconds on his stopwatch. And the earlier time, 0.00 seconds on his stopwatch. And so the subtraction there is just 0.74 seconds. All right, now all of that goes into the speed calculation. All right, so delta x over delta t gives you the speed v. So it's 2.45 divided by 0.74. Who's doing notes? Okay, Miss Caroline is doing notes today. Okay, great. On Twitter, she's doing the notes on Twitter. Sorry, Caroline. Sorry to make you do work.
Oh gosh, how dare you.
Gosh. Anyway, so your answer is 3.31. And you guys, on that problem, I specified that you should type in your answer to the nearest 0.01 meters per second of speed. And so your answer there would be 3.31. Do not try to type in the word meter per second, just the numeric part. And when we have clicking in class, where you're going to type in a number, negative 2.74, indicating a leftward speed or a negative speed, I'll tell you where to round off. Okay, I'll always do that. Exams too. So don't worry about, having to decide, well, what should I do for rounding off? I'll try to always spell that out for you, like I did in the homework. Now, there's also an example on page 10 of your e-text that you could take a look at. So make a note of that for extra reinforcement. I want to follow up with you based on this V equals delta X over delta T and delta X equals V delta T, the other version of that same definition. And I want to follow up with you concerning the idea of average velocity and instantaneous velocity. So make a note of that. We're going to talk about those two concepts, average velocity and instantaneous velocity. Now, they're both velocities, but they have a different information encoded into them, a different amount and a different set of information. And just so you know, there's a section in the textbook on average and instantaneous velocity involving the famous tortoise and the hare fable. So let's take a look at average and instantaneous. Average is based on a finite number of observations and measurements, position and time. So for instance, on the homework 1 example, there were 2 snapshots in time. So you had 2 measurements. But if you have 3 measurements, that's all right. You add them up and then divide by 3. If you have 17 measurements, you add them up and divide by 17. All right. So, but for the one that we were working on in homework number 3, the speed that we calculated was an average speed based on those 2 measurements in the problem itself. Now, what I want to point out to you is the following. You don't necessarily know anything other than his position and time at those 2 positions. So you don't necessarily know what he was doing between t equals 0.00 seconds and t equals 0.74 seconds. I mean, he might have stopped at McDonald's. Well, probably not. It's kind of a short time interval. But, he may have hesitated on his way. So you have to be able to distinguish this set of information. What is he doing at the intermediate times? The average velocity does not tell you that. I mean, it's a legitimate description of his state of motion, but average velocity does not tell you his motion at intermediate times. Let me repeat that so that you can put it into your notes. The average velocity does not encode the velocity state at intermediate times. In this case, we have 2 times. If we had 3 measurements, there's a whole slew of intermediate times between the first and the second, and then the second and the third that we don't know anything about. All right? So you have to be cognizant of that fact. So it's just like the tortoise and the hare, he could have been, chugging along like the tortoise or stopping and starting like the hare. And you don't know anything about that if all you know is just the 2 snapshots, the 2 event measurements, event 1 and event 2. Now, I'm pointing out to you that in chapter 1-11 of the e-text, there's an extensive discussion of average and instantaneous velocity and distances in terms of the tortoise and the hare fable, and we're actually going to talk about it a little more. Another place where you can see an example, a little bit shorter, is page 11 chapter 1-10. So just before the tortoise and the hare. That's the Turkey Lake Service Plaza example. Driving down the turnpike and stuff like that. Now, I want to continue with this and talk about the tortoise and the hare with a little bit more detail. And some of this detail is going to come from your textbook. So, and hey, you guys, I'm going to try to key, and Caroline and Darian, when she does the notes, they're going to try to enter into Twitter, and you can enter into your notebooks the little cues that I put in about where to find something. Maybe a page reference, or in this case, well, I already gave it chapter 1-11, a section reference. Okay, and I'll try to do that so that you can go and think, now, what was Dr. B talking about? I still don't get it. So if you listen to the YouTube and you still don't get it, all right, go read chapter 1-11 or reread it. And then if that doesn't do it for you, then find a friend and talk to them. Do you really understand chapter 1-11? And between the two of you, probably you'll get it. Or talk to Miss Maria during SI, or Miss Caroline during office hours, or me during office hours. All right? Anyways, let's get down to business. So the two kind of assumed ideas, the two assumptions in this fable of the tortoise and the hare. First of all, the hare gets going. This is a typo. I have to change this. Doctor, do you see my typo? No. Who is it that once he gets going, at any instant of time, his speed will be the same? That's the tortoise. So I have to stop the clock. Where's my cursor? Come on, cursor. Here we go. Supposed to be, once the tortoise gets going, his speed at any instant of time is the same as what will eventually be called his average speed. And you can see in this, this little graph here, the vertical scale is his speed, and the horizontal scale is the time. And you can see the way I set it up, and I made this diagram for the textbook. He starts out from rest, and he's up to half speed, and then after in the second, he's up to full speed. But it's not very fast. It's pretty low compared to the hare. But he keeps going all the way through to Dunkin' Donuts. All right? So he has a nice level speed. Now, every instant of time, his speed is the same as his average. Now, he doesn't know the average until he finishes the race, but eventually he'll be able to say, yeah, my average speed was, blah-de-blah, and he'll say, and not only that, but my speedometer read that same value almost the entire way, which is true. All right, now, the other guy in this fable is the hare. Now, this one, part B, is correct. So you can see here in my notes, I typed one about the hare and the other about the hare, but one's supposed to be about the tortoise. B is about the hare. The velocity state for the hare changes several times. Now, I just kind of made this up for the textbook, just a jumble of different times, for the hare, taking naps and slowing down and slacking and speeding up and whatnot. And he gets greased by the tortoise. No donuts for you. All right? Because his velocity state changes several times. So his velocity graph here is kind of a jumble. It's not nice and smooth like the hare down here. Another way that you can say it is in terms of the instantaneous speed, v of t. And that's one way to describe the instantaneous speed. That means the speed v at some time t. V of t is a constant for the tortoise pretty much everywhere. Nice and smooth. But v of t for the hare is all over the place. All right, so that's two different ways. Well, actually, it's three different ways. Part 5, part 6, and then the two diagrams. They all kind of are grabbing and talking about the same concept. All right, now let me pause for questions. Okay, let's keep going. There's something useful about the tortoise's graph, and hopefully you've got a little bit of room in your notes to add one more little information blurb to it, and that is the graph is nearly rectangular. The only place where it's not rectangular is down here, where he's actually getting up to speed. But other than that, he's nice and flat. All right. So this is a fairly realistic picture of the tortoise burning his way through all the way to Dunkin' Donuts and getting those donuts. Now, what we're going to do is make an abstract graph of constant velocity versus time. And it's going to look like this. On the vertical axis is going to be the velocity. And on the horizontal axis is going to be time t. So let's get to an example of that. A basic velocity versus time graph. And this one's going to be representing somebody that's just going along at 1 meter per second. 2.24 approximately miles per hour. Okay, so the vertical axis represents the velocity. So that means positive numbers, the upper half of the axis, you're graphed up there if you're moving to the right. And then the negative numbers, so that's down here. Now, this graph is not plotted up down here, but if we had something that was moving to the left, it would correspond to negative numbers on the graph. All right? Now, what we have is something that's up in the upper half of the graph. Now, the horizontal axis represents time, and usually we'll anchor it to time t equals 0. You know, just like out at Kennedy Space Center, t minus 30 seconds, 29, 28, 27, and the countdown to time t equals 0 when they light the rocket, and then they get liftoff. Time t equals 1.2 seconds, liftoff. Okay, so we're going to anchor our stuff. Is that you?
Yeah, that's me.
Okay. All right. We're going to anchor to t equals 0, 0. And let's do our graph out for 2.5 seconds. All right? Just for something to talk about, to make it a cinchy example. And so the object that we're going to study is an object that has a constant velocity of 1 meter per second rightward for 2.5 seconds. And so its graph is this horizontal dashed line right up here. All right, so, and you don't have to make it dashed. You can make it, circles or little waves or, whatever you want to do. Or just a plain, straight, solid line. All right, and that represents the velocity of 1 meter per second. Now, that is similar, that is similar to the tortoise's graph on page 13 of your textbook. All right? And our graph here is kind of idealized. The tortoise's graph was a little more realistic because the very first slot was half speed. And then all the other parts of the graph were full speed, not very high, but at full speed for the tortoise, all the way out to the end. This one starts at full speed and finishes at full speed after time t equals 2.5 seconds. And the reason that this is a useful graph for us, among other things, is that it encodes all the instants of time visually. In other words, the homework problem where we had 2 snapshots, 2 sets of measurements. We didn't have all the intermediate times. That you can only do a table with that. You can't really make a picture like this because you don't know the intermediate times. You don't know what the velocities are. But this one, if you say I have a constant velocity, you can make a graph like this. And this graph encodes all the instants of time between 0 and 2.5 seconds. All right. So that's a basic thing. And so item number 6 is actually kind of an abstract concept. By the way, this graph paper, in this graph, you're not graphing x and y coordinates like regular graph paper. I mean, you use regular graph paper for this if you want, but the vertical axis is marked out in units of meters per second, not meters. And the horizontal axis is marked out in units of seconds, not meters. Right? So this is kind of an abstract graph. It's not a set of photos. I mean, if you have regular graph paper and you take like a series of strobe photos, you can put the position from your strobe photos on your graph paper, and that's a fairly good representation, but that's not what this is. All right? This is an abstract representation of the motion of this particular object. Number 7, shade in the rectangle between the graph and the time axis, and between 0 and 2.5. So that's right in here. Right? So make a rectangle, and then kind of shade it in. Just for emphasis, I mean, you don't have to shade it in if you don't want to, but definitely make a little rectangle. And then I'm going to pose you here in item number 8 a very important question. If, as we say, the graph's straight line represents the object velocity nicely, and it does, then what does the enclosed rectangle? That's part of the graph too. What does that represent? Right? So that's an important question, and we're going to answer it. And you're going to see that now you guys that are engineering majors, you hush. Okay, so you guys got to hush your, okay. Zip. Zip. That whole row, that whole engineering row, no, zip, zip, zap. We'll get to it in just a second here. All right, so now we got a rectangle here. Hey, you guys, how do you calculate the area of a rectangle? Yeah, length times width, base times height. All right, so go ahead and write that down. Just the good old area. What are you, like a computer science major? Real estate? Dude, you're burning my grits. Gosh. Genius time over there. All right, so now the area is base times height. All right, in this particular example, the base is 2.5 seconds. And notice it's not a distance. It's a duration. It's a temporal measurement, 2.5 seconds in this example, all right, which I made to be fairly cinchy. And the height is just above the above the horizontal axis, the time axis, 1 meter per second. And that's not distance either. That's a speed. All right? So the area, let's see, the multiple of the area, let's see, you multiply base times height. And if you feel like it, is there anything in there that you are tempted to do to simplify the expression? What? You could cancel seconds. 2.5 seconds, that's in the numerator. And then in the speed half, the second half, it's meters per second. So that's like in the denominator, and those two cancel. So go ahead and put the chop on those two babies. And that means that your answer for the area is a distance on this abstract graph. And therefore, it is kosher for us to answer number 8 in the following way. We can interpret the shaded area between the graph and the time axis as a distance, the distance traveled from the start, whatever the starting point is, to a new point 2.5 seconds later, when it's moving at a steady, constant 1 meter per second. Now, let me ask you a mental IQ test here. And I don't have a clicker question for you on this, but let me ask you, what is there about this graph that you see here, and it's shaded in and stuff, what about that tells you that you have a uniform and constant velocity? What feature of that graph tells you that? What straight? I see a lot of straight lines there. Which straight line? The dashed line is straight, and what about it? It doesn't change, but what if it was tilted? That would be a straight line. Could you use a tilted straight line to represent uniform, constant velocity? The engineering department over here says no. Does anybody agree? And what you were thinking visually, but your words weren't sufficient to your what you saw. How would you describe it? If it was tilted. If it was tilted, the velocity would change. So the full answer, see, your eyes see it, but your concepts are still a little bit lagging, which is why you're in this class. That's good. So what your eyes could tell you is that the feature of this graph that shows it is uniform velocity, constant velocity, is that the graph itself is flat. It's a straight line that is flat. It's not tilted upward. It's not tilted downward. All right? So, last comment for you is that all of this jives with the distance formula. Delta x is equal to v delta t. Delta x is how far you go, or the change in your position during the elapsed time delta t. And if v is a constant, 1 meter per second or 25.3 meters per second or whatever it is, if v is a constant, then you have a rectangle. On the velocity graph, a uniform velocity object will show up and form a velocity rectangle, the area of which is the distance traveled from the initial point to the final point, whatever that happens to be. So if this guy started, this graph, here's another thing you can make a footnote to history. This graph doesn't tell you anything about where he is in space. It doesn't say where he is in Dubuque, Iowa, or New York City, or Shanghai, China. All right? But what it does tell you is if you did know where he was in Dubuque, you would know that 2.5 seconds later, he'd be 2.5 meters away from where he was at the start in Dubuque, Iowa. So, to figure out exactly where he is and where he's going and how long it's going to take, the velocity graph here is a good tool, but it's not the only tool. And you have to write a lot of extra sentences to make a full description. But it's a good start. It's a good tool. Now, I have an iClicker 2 question for you. So turn on your clicker, please. And if you are bringing your clicker for the first time, hold the power button down until it starts to flash, and then type in BB. Did you get BB for the frequency when it started?
I don't know.
Okay, you probably didn't. You just didn't even look. It's all right. Don't worry about it. I'm pretty sure I set it to BB.
Okay.
All right, so after you get that, it'll say, let me try this again. Okay, this one, we just set up a new database because of the fiasco last week So it should say go nitro and then ready. All right, when you get that, that means that I can hear whatever you click with your clicker. It doesn't mean you're registered. Bonus points in the grades page means you're registered, and nothing else. Nothing else means you're registered. All right, now this is a serious question. We don't have any goofy Chuck Norris questions today. All right, here it is. Go ahead and start. Yeah, there it is, BB. Good. Okay. Each dot represents a snapshot of the position of an object moving from point A to point E, with elapsed time delta t equals 0.1 second between flashes. So this is like a strobe photo. But which statement is correct? Ooh. Actually, this is kind of interesting. We're getting a little bit of a, this is interesting to watch. Okay, 20 seconds to vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ching. Okay. Go to computer. Let's let them see this. Okay. Now, most of you, there's the distribution of answers. Now, notice that there's a decent amount of people answering each option. Now, most of you, 60%, answered B. And actually, okay, go back to option B is the correct answer on this one. Okay. Now, here's, did you get option B?
No, it says no base.
Yeah, that means that, bring it up here to Caroline. No base means you're not on the frequency. Okay. Anyways, so what is it about this graph that shows you or that tells you the object is slowing down? Think about it. What is it? What would you say is it that tells you? What do you think? That's right. It's traveling less distance with the same amount of time. In other words, between each adjacent dot, it's a tenth of a second. And these dots over here, it's just poking. It's just poking along over here. But over here, it's blazing. All right? So that means it's slowing down. Over the space of, let's see, 1/10, 2/10, 3/10, 4/10 of a second, it's slowed down pretty good. All right? So that means it's slowing down. So that's visually what the strobe image or the simulated strobe image shows you. All right? Now, what we're going to do now is the main objective for today's class, and that is we're going to draw a velocity graph for something that's accelerating, something that's slowing down. All right? Now, the velocity graph that we just did for object with uniform velocity is pretty cinchy. Just base times height, v delta t. No great shakes about that. But for something that's slowing down, it's going to be a little bit different. All right? Now, to do that, we have to put up a definition for acceleration. Because to figure out the distance for the distance rectangle, we had to know the definition of speed and velocity, delta x over delta t, and then we had to know its cousin, delta x equals v delta t. Now, a equals delta v over delta t is going to give us indirectly an interpretation of the velocity graph for something slowing down. So the whole idea of acceleration is simply this. How much does the velocity change in a given amount of time? A certain elapsed time, delta t. So here's your formula. That's basically the definition of acceleration. It's the quotient of the change in the velocity divided by the amount of elapsed time. All right? So it's like 5 miles per hour per second. So if you're out on university and you see somebody that's driving like a maniac, like 3 in the afternoon or 4 in the afternoon. Now everybody here, I don't see any maniacs in here. So I know this doesn't apply to anybody here. But I know you've probably seen that driving away from campus at about 3 or 4 in the afternoon on university. There's an awful lot of maniacs out there. And they're accelerating, they're changing lanes and all kind of stuff. That's all, they're changing their velocity state. Okay, there's a lot of delta V. And if they have a good car, the delta T's are fairly small. If they have a beater, they can't really do much acceleration. So they can go from 0 to 60, like for James Bond, it's 0 to 60 in 6 seconds or something like that, right? But if you have because that's a kind of a hot car, is a nice rig. But if you have a beater, it's 0 to 60 in 4 days or something like that. So, but anyways, in general, it's delta V over delta T. And here's the cousin to it. And this is just cross multiplication. Get delta T over to the other side. Delta V is equal to A delta T. Now what that means is that you can, if you know the acceleration and the amount of elapsed time, you can figure out how much speed you're going to change, how much delta V you're going to get. All right? Now, the parallel example to that is delta x equals v delta t. This one's not the same. This is not a distance formula. This is a change of velocity formula. Right? Not change of position, but change of velocity. A delta t. All right? Now we're going to use that. So make sure you have that in your notes. And here's the velocity graph in which we're going to use it. All right? So go ahead and draw a velocity graph again. And go up to 3 meters per second vertically. And we'll just stay positive. All right. We could do the same thing with negative if we want. Leftward motion, that's fine. But let's stay positive. And let's say that in 4 seconds, it's down to the time axis. That means v equals 0. Okay, so the dashed red line is the graph itself. And you can shade in between the graph and the time axis and actually the v-axis. And so its states start, it's tilted. Okay. What is your name again? Frankie. Okay. Frankie, here's where the tilt angle comes in, because if you're not accelerating, you're flat. Okay? But if you are acceleration, you've got to tilt either, downward like this, downward to the right, or up to the right if you're speeding up. Okay? So this is slowing down to v equals 0 after 4 seconds. Go ahead and shade in the triangle. Let me go back to that. Hold on. Oh, sorry, I bleeped it up. Because I went through it a little bit too fast. Okay, so just get that set up. Okay, this represents an object that's slowing down. And we have the strobe image. That's an object slowing down. This is another way to look at an object that's slowing down. That strobe image, you could have put on a piece of XY graph paper. All right? This you can't. But it also describes the velocity state for all the instants of time between t equals 0 and t equals 4 seconds. All right? Now, the area of a triangle. Do you remember the formula? Yep, 1/2 base times height. So just go ahead and write that down. And hopefully this will be able to interpret this area as a distance too. Let's see if it works out. And if it is, it is a triangle. We have we have uniform slowdown, slowing down by 3 meters per second in 4 seconds of slowdown. All right, area is 1/2 base times height. So, all right, the base is 4 seconds. The height is 3 meters per second. So go ahead and pencil that in. All right, there's your actual numbers. And again, on this calculation, you have that factor 1/2 because it's a triangle. But notice that you can cancel seconds from the base and per second from the height. No, it's the same as last time. Yeah. Slightly different formula, but we can still cancel. That's good. All right. And so we're going to have a distance, so that's good. But I want to show you something, and we're going to use the numbers to derive a formula here. All right. So before you jump to anything else, let's just rearrange it slightly. Let's park that 1/2 underneath the change in the speed, 3 meters per second, because that's how much, that 3 meters per second, that's your delta V. So you can just add that to the footnotes. 3 meters per second is A delta T. All right. And we're going to use that to form a formula. But let me ask you this. This quantity, 3 meters per second, okay, that's delta V. What is 3 meters per second divided by 2? What is that quantity? A bunch of speed divided by 2. Repeat. That's the number. It's going to be 1.5 meters per second. But conceptually, what is that? No. No. It's the average speed. Look at it. Initial is 3, final 0, add them up, divide by 2. That's your average. And that's what we've got here. All right, so that's an average speed. So go ahead and write down delta T. That's your base. All right. And then average speed. That's the height divided by 2 for this triangle. Right? Now, if you have a different shape, if you got a little bit of curve to it, you got to do something different. But for a regular triangle, nice uniform slowdown. Yep. Now, the average speed is also delta V. Oh, hey, wait a minute. Average speed times elapsed time. That's total distance. So in this equation right here, put another little equal sign right here and say total distance from t equals 0 to t equals 4. Okay, total change in position. It's just average speed times elapsed time, so we know what that is. Speed times time. That's easy. Right? So that's your form. But now look, that average speed, this is where we add value. A delta T divided by 2. Remember, it's delta V in the numerator and then divide by 2. So this average speed here is the same as A delta T over 2. All right? Let's put that in there. So your distance is delta T times A times delta T again divided by 2. And hey, you guys, that is expressible in a fairly simple formula. 1/2 AT squared. And in this one, Frankie, we're replacing delta T with just a plain old T. All right? Whatever so we're assuming that you start at 0. and then t is going to be the same as delta t. All right, and the distance is 1/2. And that represents the distance traveled from t equals 0 when it was really booking to t equals 0 when it finally stops. All right, that's the amount of distance you have traveled. You know who figured this out for the first time? Professor Galileo, who is the boss of us. He's my boss too. He's my research director. So in general, and I like to call this formula the distance triangle formula. All right? And you can use it wherever you have uniform acceleration. The same slowdown. Okay, so in other words, if you have a velocity graph that's a good, straight, tilted line, whether it's slowing down or if it's speeding up, either way, you can use this formula. If you have something that's a horizontal line, uniform velocity, the distance rectangle formula, v delta t. This one, 1/2 at squared. Now, I will bet you $20 that if you interrogate 20 engineering majors that supposedly know calculus out the wazoo, although I'm sure you guys know this interpretation, they probably could not tell you why this formula is there and why you interpret it as distance. But now you know the full story that the engineering majors do not or might not. And that is that in a velocity graph, the area underneath the velocity graph, no matter what the shape, triangle, rectangle, or any other shape, you interpret as a distance traveled. And so my wonderful students, these are the two formulas that we will use. And you know this movie, I still haven't gone to see it, Hidden Figures, with the ladies that work for NASA and that crank, like everybody did back in the olden days, like in World War II. And up to about the middle of the 60s, they did all those space-time trajectories by hand, and then eventually started backing up by the computers. Now they just use computers. But all the stuff that they were doing by hand was distance rectangles and distance triangles. That's it. And what we've done here today together is a little bit of calculus. So you can go home and tell your folks tonight, yeah, we did calculus in physical science today. Visual calculus, we did it in terms of the velocity graph. Didn't have to do any fancy dancy math formulas and stuff. Just 1/2 at squared. But it's kosher, it is righteous, and it is what they did in that movie. So I got to go see that movie this weekend. How about you? All right, you're dismissed. Homework is to finish reading chapter 1. Nothing else. I'll give the guys a break this week. How come you have so many colored pens? Yeah.
So are we going to be using derivatives to calculate the rest of it in the rectangle, or are we just sticking with rectangle?
No, well, visually we'll be doing derivatives. We just did an integral here. But officially we're not supposed to do any calculus, but this doesn't count as official calculus.
Okay.
But the math department would never do this, but we do it over here. Or at least I do it over here.
Right.
But yeah, I'll be mentioning derivatives from time to time. So, yeah.
Thanks.
When's your register?
I picked up this class at the deadline.
Yeah, and you're one of the guys back there in behind the fifth row.
I'll sit up front next time.
Yeah.
But is there anything like in specific that you
what's your
said over
last
the
name?
first 2 days that was like crucial?
Yeah, you want to review the syllabus.
Okay.
And we had some physics instruction on Thursday. Okay, now all that's in YouTube. Are you in web courses yet? Okay.
because it says
The
you were absent,
PDF,
so I don't know why it's being
the
weird. Maybe just
syllabus
go
is on PDF
'cause you're on
format
here, so I
in
don't-
YouTube. So,
That's weird.
yeah, so dip it, or excuse me, the syllabus is in PDF format on web courses.
Do you know
It's
what
on
it
the
means
front
if
page.
the name is in red? What does that mean?
What's that? That means unregistered.
Unregistered?
Yeah.
Okay, maybe try registering it again. I don't know,
So
maybe it
just
didn't go through or.
To the iClicker website?
No, on web courses.
Dude,
there's
no.
There's a tab that says iClicker, and just click
Also,
on there and type in your
what
serial code, and
calculator
it'll go.
do you use this class?
Anything scientific calculator's
That's why,
fine.
yeah.
Have you got one?
Just so
Alright, no
basic
worries.
science.
Thank you.
Sure
Yeah.
thing. Hi. Yeah. I read
Are you also a newbie?
Yes.
Okay.
Are we able to make up for the things
Homework
that we
one?
didn't?
Okay.
No, but it's just 5
did you do it
points.
on the,
Don't worry
web
about it.
courses website?
It'll be a little bit of a mosquito bite by the end of the semester.
Okay. What
Yeah.
about
Right, yeah.
so like I guess the
But so-
activity
Right, yeah.
during the class with the iClicker, does that count as?
Not yet. It's practice today until January 31st. Read the syllabus and it'll explain it to you, okay? So, read, do you have the textbook yet?
Not yet.
Okay. Your homework for tonight is
Yeah,
just to
you're
read
fully
up to the end of chapter
registered, so I
1.
Okay, I'll
Which
get
today's-
the
You're good.
textbook.
You
Do
got
they
points
have an ebook?
Yeah, it's an ebook. It's only an ebook, so
Oh,
you
okay.
can't buy it in paper and stuff.
Okay, and where is the iClicker? Do they sell it in the bookstore, or do I order it online too?
Bookstore, CS, CBNS, just different places. It's got to be one of these.
Can I take a picture of it?
Yeah.
Yes, you
Like
can.
make sure to go to the bookstore to get a sample this week because of so it's ABC.
Yeah.
Thank you.
Yeah,
Okay.
I got you. Okay. That
Hey.
was perfect.
Hi, I messed up when I got your homework that wrong. Is there any way to get access to the question just for practice purposes?
You didn't get any attempts in?
No.
You forgot it.
Yeah, I thought it said 10:30 p.m. So I was just like, okay, so I have time. So is there any way I could get?
No,
access
but
to-
if you have a friend, do you have any friends in class?
No.
Okay, make a friend, and then they can let you look at theirs and stuff. And it's a good thing to do, to have a friend to study with. So, all right? Because I wish I could, but they just Canvas is not so.
Yeah.
It's not so easy to use for stuff like that. It used to be you could do something, but
Okay, thank you so much.
So-
So,
yeah. But what? Did you take notes today?
yes.
That's the main stuff. That was the main. The other two questions were pretty cinchy.
No, I was-
But number
is this for
3
this
that we
class I
went
can
over
just leave it
class.
open? Oh,
Okay, thank you so much.
And then I'm supposed to-
Yeah.
So I was about to, but then-
Chad, good. Chad Hollander, very good.
Thank you.
The first day,
Yeah, is the book?
get the syllabus in web courses. The book is an ebook.
I'm like, I want to put some on my
Is any homework from the book?
Well, yeah. I mean, today finish reading. That's the homework assignment, chapter 1. So, yeah.
I'm Jason.
Jason, good. The engineering man. Oh, you're the real estate man. Yeah. So, did you have calculus in high school or something?
Yeah, a long time ago. We're actually friends. I didn't know he was in. I told him.
Yeah. Oh, you blurted it out?
Yeah. Well, I knew one.
Yeah. No, but it's kind of cool, and it really is true. I bet if you ask 10 engineering majors, maybe 1 or 2 would understand that
Most of them
facet
don't
of
know
it.
any concepts. It's all just how to.
Formula. Yeah. That's the hard part, the concepts. So, all right, fellas, good.
Thank you.
All right.
I'm Anastasia.
Yeah, right. And I have your unit right here. Let's see now. Anastasia, what was your last name again? Okay, you're in the noon section, right?
This section. Yeah, well, I'm in this section.
Second section.
The first one.
You're in the
She was sitting in
10:30?
front of me. Yeah.
Dude, why didn't you come up
I
for
was
it?
scared.
I was scared. It's okay. Come
Yes,
with
she
me,
looks.
And
she
then I'll
loo-
grab it for you.
She looks pretty scary.
Yeah, I know,
These two, yeah,
I
right.
know.
Anyway,
You can check it. What's
okay,
on
let's register it.
Okay. How do I?
What you do is, what's your last name again?
Portier.
Oh, that's right, Poitier. Is that how you say it? Are you from Bahamas?
Yeah, my family is, yes.
Yeah.
Oh, my
Good.
That's it.
POI. Right here. Okay, now add, and then add this number. Yeah, we usually, it's always fun to, oh boy, recording all this. Good going, Dr. B.